Electricity is an essential part of our daily lives. It powers our houses, workplaces, and trains. Unfortunately, a lot of this energy is lost as heat due to resistance when we run currents through metals. To really understand what's happening when we run a current through a metal, we need to look at the atoms and electrons inside. Metals are generally considered to be good conductors due to their structure. They have a periodic structure called a crystal lattice. Metallic bonding is such that the ions can be pictured as surrounded by a sea of electrons. This is because the ions effectively give up their valence or outermost electrons, which are then shared among the lattice. Whenever you apply a voltage across a metal, there is an electric field, so the electrons feel a force. They therefore drift from one end to the other, creating a current. Metals are not perfect conductors, however, as some of the electric energy is lost to resistance. The movement of electrons in a conductor is obstructed by collisions between the electrons and the metal ions. Resistance increases with the temperature of the metal. As the temperature increases, the thermal motion or kinetic energy of the ions increases. They start moving back and forth, resulting in lattice vibrations. These vibrations are the main cause of collisions between the ions and electrons. As the atoms in the metal are always moving, there is always some resistance. Imperfections in the lattice also increases the number of collisions. Resistance means some of the kinetic energy of the electrons is converted to heat. This limits the efficiency of electrical systems. Ideally, we'd like to remove or minimise this energy loss. In 1911, it was discovered that under certain circumstances, some metals have no resistance. In fact, many metals below a certain critical temperature will allow current to flow free of resistance. These materials are called superconductors. Here is a graph of resistance versus temperature. As temperature decreases, you can see resistance decreasing steadily, but at the critical temperature, it drops sharply to zero. At very low temperatures, the lattice vibrations slow down, and these vibrations and impurities no longer have an effect on the motion of the electron. This only happens when electrons pair up into what are called Cooper pairs. The Cooper pairs move freely through the superconductor and are unaffected by resistance. Superconductivity can be explained in low-temperature superconductors by BCS, or Bardian-Cooper-Schrieffer theory. It explains how Cooper pairs form and why this means they can travel through a metal with no resistance. To truly understand BCS theory, you need to know some quantum mechanics, but you can roughly visualize it as follows. As an electron moves through the lattice, the positive ions are attracted towards it, distorting the lattice. This creates an area of temporary excess positive charge, which can briefly attract another electron towards the first. The lattice distortion allows the electrons to form a weak attraction. Once the Cooper pairs are formed, the lattice no longer has enough thermal energy, as the lattice is very cold, to scatter the electrons in different directions. To scatter the electrons, which would result in resistance, the lattice would have to break the bond between the electrons in the Cooper pair. This is how the pair can carry the current through the metal with no resistance. The fact that current can travel through a superconductor with no resistance has a lot of consequences for the material. Most obviously, no electrical energy is lost, so superconductors are very energy efficient. One other consequence, which is not so obvious, is that superconductors do not let magnetic fields penetrate their interior. When they are placed in a magnetic field, the field induces currents in the surface of the superconductor. These currents produce a magnetic field which exactly cancels with the exterior field in the interior of the superconductor. This property is called superdiamagnetism, or perfect diamagnetism. This exclusion of the magnetic field is also called the Meissner effect. It can be used to levitate a strong rare earth magnet. To the magnet, the superconductor looks like another magnet with an opposite magnetic field, or pole. so the magnet is repelled from the superconductor.